All right, in terms of the contents of the course, so we're going to start with just some introductory remarks and discussion on the expanding universe. So you can think of the first half of the course also as, like laid out in most textbooks, you first think about the universe in the homogeneous approximation, as we'll discuss. And we'll talk about, well, wait a minute. So the contents of the universe, how it expands, dark matter, dark energy, radiation, the different eras of the universe. We'll talk about the early universe in some detail, the very early universe, where we have to think about some statistical mechanics and thermodynamics of electrons and positrons and so on. A little bit on nucleosynthesis, how the light elements were formed. And then we'll talk about some big puzzles in cosmology, most of which we think are solved by the theory called cosmic inflation that we'll discuss. And then we'll move on to sort of the kind of inhomogeneous universe. So we have to think about when things are not quite smooth, how do they evolve? Okay, and so we'll see how small deviations under some circumstances tend to evolve to become large deviations. And ultimately you can get out stuff like galaxies and stars and planets and so on. We'll talk a bit about the cosmic microwave background radiation and its fluctuations. And then towards the end, we'll have some freedom. We'll talk a bit about like the quantum initial state of the universe and potentially other topics depending on how much time we have. Okay, is that okay? Well, we'll see how far we go. Okay, I don't want to go too fast, but are there other topics that anyone was hoping for or questions about that? Sure. Okay. Right, so probably what I'll do is I'll put like a list of like possible topics we can, so each should have their own individual subject that you can go into. And I usually it's something like say a 4-page report on this and maybe a brief presentation to the class, 5 to 10 minutes, something like that at the end of the course. Okay. So I'll put like, yeah, possible topics, but you're free to choose from that. Or you're also free to pick your own separate subject if that's not what you want. Other questions? Okay, so yeah, so cosmology is a topic where if you ask the average person what it's about, well, it's not cosmetology, although I recommend somehow every April 1st, Ken Olam decides that it's the Institute of Cosmetology, so you can check out that website if you Google it. There is apparently a Mark Hertzberg who's a doctor of, I don't know, facelifts or something, so that appears on the website every, let's not worry about that. So cosmology, beyond that, is often thought of the subject of the very large and the whole universe, okay, and the contents of the universe. So those are sort of the things that come to mind. And that's not a bad description. But cosmology is, in some sense, more than that because, you know, in a way, half of our time is spent thinking about things that like Tony and others are interested in, which is things about particles. And when I tell that to the average person, well, why do you care about particles when you're interested in the whole universe? Aren't you looking at the wrong thing? It's for a very basic reason that the whole thing is built out of these little particles. So of course you have to worry about particle physics ultimately if you're interested in cosmology, though it depends on the aspects of cosmology you're interested in. Okay, so if you're doing things purely, say, structure formation, how things evolve due to gravity, well, it doesn't matter too much usually to know, say, what the particles are doing. But if you're interested in, say, a question like, what is the dark matter? You're asking a question about what is the particle physics of dark matter. If you're interested in the question whose answer we don't know, which is why there's more matter in the universe than antimatter, that's a good question in cosmology. That presumably happened due to some asymmetry between matter and antimatter in the early universe. And so there should be some Lagrangian and some particle physics explanation that underpins that, for which people have ideas, but we don't know which is the right one. If you're interested in the very early universe, like cosmic inflation, you're certainly interested in ideas connected to microscopic physics. We could call it particle physics, broadly speaking, and so on. Okay, so we naturally spend sort of half of our time thinking about things very on big scale and maybe half on very small scales. They're kind of interconnected in this way. And so anyway, cosmology means different things to different people. On the theory end, it's also, if I push that point a little further, it's also connected to exploring new physics. Okay, so the very early universe we think is not in detail understood by standard known physics. So it's an arena in which we say, well, we need some new ideas to explain what we see today, because they're not explained by the standard rules. Certainly dark matter fits into that category, and the matter-antimatter asymmetry fits into that category as well. Okay. But then again, cosmology, some people refer to the topic of, maybe they call it physical cosmology, which is a kind of funny name. But sometimes that just refers to, as I said, like expansion, development of galaxies and so on. And that's a little bit more, you could say, standard physics. Okay, so it's not always that you're speculating about some new physics. So there's a mix. So anyway, welcome questions, comments, thoughts about any of this. Okay, so for the first class, let's see, is this thing recording? We're going to talk start with the homogeneous universe. And, oh, I should mention that next week we're going to have to introduce some essential tools of general relativity to describe things in detail. But in this class, we'll see that we can get pretty far with just Newtonian gravity as a starting point. And as we'll discuss, Newtonian gravity also describes the expansion of the universe. It's not some new thing from general relativity, although historically it wasn't new, but Newton could have predicted it himself if he bothered to. All right, so anyway, we'll get to that in a minute. Okay, so let's start with the first point, that the universe is very homogeneous and isotropic on large scales. Okay, so right, homogeneous means it looks the same at each point in space, and isotropic means it looks the same in each direction. Okay, by the way, my notes I can also upload to Canvas. So let's unpack this a little bit more. If I look at, say I take a piece of the universe here, right? Saying things are homogeneous and isotropic, of course, sounds a little funny, where Earth is not a homogeneous place and so on, and nor is our galaxy. Okay, but so large, therefore, you have to go to even much larger scales than even our own galaxy. Okay, so many, many galaxies. So for example, let's say we pick 100 megaparsecs. Okay, so parsec is about 3 light years. And okay, so let's say you have a box here of size 100 megaparsecs. And our universe is a few gigaparsecs of the observable universe. So this is still a smallish little chunk of the universe. It's not the whole thing. And let's say you start counting up galaxies in this thing. Okay, so there's a bunch of galaxies here. So forth. And let's say you then go and move to the next box, chunk of the universe, also size 100 megaparsecs. And you count up the galaxies there. They're going to look a bit different. They're all just spread out in some fashion. Okay, I'm not going to try to be too accurate here. But basically, if you conduct these large-scale surveys and you count the number of galaxies in one box, giant box like this, and another box of the same size, you find the number of galaxies is almost the same. Okay, and so that's what it means to say that on large scales, it looks almost homogeneous, though not exactly. So if this is box 1 and this is box 2, the number of, say, galaxies in box 1 ends up being something like the number of galaxies in box 2 with a correction that's like order 10 to the minus 4 on these big scales. So it's surprisingly uniform. Okay, so that's what we mean. So any questions or comments on that? And then the isotropy, well, we can see it in the galaxies if you look at different galaxies from one direction to another as well. But we can, an even more precise version of that comes from the cosmic microwave background radiation, which we'll talk about later in the course. So we don't have to get into it too much now. And there, we just, if we're standing here and we look out and we collect all this radiation coming towards us, for reasons we'll discuss later, these photons that arrive here, they're basically thermal, they have some temperature. So there's a temperature over here, well, let's say T1 again, and a temperature over here, T2, the temperature of those collection of photons. And these temperatures also agree to high precision, in fact, even slightly better than this. In this case, T1 basically equals T2 up to 1 part in 10 to the minus 5. And doesn't matter what direction you look. Okay, so that's the statement that it's isotropic to high precision. Yeah. You want 10 to the minus 6 here? I think it's 10 to the minus 5. You're, oh, why is this one smaller than that one? I mean, okay. So we could ask like, why is it 10 to the minus 5? So, that's a good question. The short answer would be, okay, the deep answer is no one really knows. So this number, the way our works its way back all the way, so this is happening at an era we'll talk about later when the universe is like 380,000 years old, and there are these 10 to the minus 5 level fluctuations. Okay, so we can take this as a fact. That 10 to the minus 5 level fluctuations, we can trace it back to earlier and earlier and earlier times, at least in our mind. And then we'll go all the way back to some early, very early time that should have selected this number 10 to the minus 5. And we don't know why the universe picked that particular number. So for example, later we'll talk about inflation, if that is the theory of the early universe in that context. And in the context of inflation, you have to hardwire into your theory the number 10 to the minus 5. You have to put it in by hand. So we don't have a deep reason as to why I picked that. Okay, but for now, I'm just saying that these are these observations that we currently have. So maybe we have some ideas as to why, if inflation is true, why that number is somewhat small, but we don't know exactly that. If you could explain that, you will be very famous. Okay, so given this, what we do, and what we'll do for a few lectures then, is that we don't pay attention to the 10 to the minus 4 or the 10 to the minus 5. We can come back to that sort of later in the course. We just think about the fact that it's essentially uniform. Okay. So we're going to treat the universe as perfectly homogeneous and perfectly isotropic. Is that all right? And you can see when you're interested in things on large scales, you're going to get answers that are correct to high precision. But of course, you may be interested in galaxies and clusters of galaxies and scales beneath that for which you care a heck of a lot about these deviations. So it depends what scale you're interested in. Okay, so let's talk about the homogeneous universe then. We'll come back here. Okay, so we'll just note that Hubble discovered the expansion. Let's say from the redshift of distant galaxies. Okay, so we can think of this as essentially the Doppler effect. We could be a little fancier about it in general relativity, but essentially the Doppler effect. Things moving away from you look red, and the faster they're moving, the more red they look. Okay, so the red could be used to learn about their velocities. So here we are again, or here's Hubble. And so then just the statement of what it implies would be if you have a bunch of galaxies here, and they're moving like this, okay, it means that at later times, they look like this. Okay, the same galaxies just moving away from us. Okay, so the expansion of the universe is not some bizarre thing necessarily, and we're going to describe it, at least today, in the Newtonian language, so we're not even going to necessarily say the words expanding space, though we can use that language in general relativity. And it will allow us to actually understand certainly relativistic phenomena better. But from this down-to-earth point of view, there's just a bunch of galaxies here. These are just their velocity vectors. Okay, and this is what we observe, because of course we can only measure this now, or for the last 100 years, but essentially now. And then the red implies this picture, and so physically it implies that later it would look like that, and earlier that would be all further bunched up. Okay, literally just spreading out. Okay, so it's kind of like a gas of particles as an expanding gas, but gravity will play the crucial role in the evolution of this gas. So it's not just a free gas. And so you can imagine under Newtonian gravity, whilst it's going out, they're gravitationally interacting with one another. So the ones out here, say this one here, is going to be pulled by all these ones. So it's not going to want to go out too fast. It's going to want to slow down. And how it slows down is something we have to think about, how it might slow down. Is that all right? Yeah, so that's what the expansion of the universe is. And as far as we can tell, these little arrows, I should say, that where the galaxies are, let's say, we don't know of an end to that. So I could keep drawing these galaxies forever and ever as far as we know. So that's another important point. That's, by the way, encoded in the idea that it's homogeneous. So if it went out like this and then stopped, like there was a boundary, that would be inhomogeneous because you'd have mass and then no mass. So that would be an inhomogeneous thing. So as far as we know, it just keeps on going. But this picture changes to that picture at different moments in time. To get from a picture like this to a picture like that, where let's say that each galaxy, say this gap here has gone out, say twice as far, a factor of 2. Today it takes billions of years, roughly of order the age of the universe. It would take to go from there to there. In the early universe, as we'll discuss later, for distances between things to double, in the early universe takes a short amount of time. I mean, if the universe is 1 year old, it could not have taken a billion years, so obviously that can't be true. But typically it takes on the order of the present age of the universe, the universe's age at that time. We can discuss that as we go. All right, but any questions about this picture? Everyone's comfortable with what it means for the universe to expand? Oh yeah, I actually put that down. Well, can I define that in a minute for you? Just so I want to be clear as to how to define it. So I need some equation. Okay, so because you said, good question, you said expansion velocity, but there isn't a unique velocity because the different galaxies will move with different velocities. Okay, so the ones that are further away move faster, so I probably should draw these arrows bigger than the ones that are closer. Yeah, the ones that are further away more red, they're moving faster. So they move at many different velocities. An object in the homogeneous approximation that's right next to us just over there, is hardly moving at all. And the ones that are far away are moving super fast. But however, there will be a rate at which we can define this thing. Something has units of just 1/time. That will be the Hubble rate, and I'll define it in maybe 5 minutes. Okay, and that will be a number that we can assign to the whole thing. Yeah. So there's a rate attached to this thing, a rate of expansion. All right. And oh yeah, and just to be clear, right? More or less, the size of these galaxies is staying fixed as the universe expands. I just say that because there's always some, I don't know, a philosopher or someone says, if everything's expanding, how can you measure that? No, it's the distance between things gets bigger, but the objects stay put in size. Atoms don't get bigger as the universe expands. Atoms and whatnot are set by this, like this Bohr radius, whatever, is set by fundamental constants. And it's just a fixed number, for sure. All right. So anyway, let's discuss using Newtonian gravity. And in fact, so as you know, Newtonian physics works well when things are moving slowly. And so the very early universe is not going to work. Things will be moving fast. The universe will be dominated by stuff like photons and so on. So the Newtonian description is not going to work. And even more recently, as we'll discuss, we have to deal with dark energy, which is also not described by Newtonian physics. But and we'll lay out the whole history later on. But it turns out from the universe when it was about 70,000 years to about 6 billion years or so, the stuff in it was sort of more boring stuff made up of slowly moving stuff, which is well described by Newtonian gravity. So this will actually be accurate for a big chunk of the universe, history of the universe. So it's an important thing to do, and it also helps to get some idea as to what's going on. Okay. All right, so I'm going to just come to this picture again. So let's say here's the origin, or that's where we're standing. And I don't necessarily want to draw individual galaxies per se, but when we're going to think of things as homogeneous, so we're surrounded by a kind of fluid, if you like, so some material that's spread out more or less evenly. Okay, and then what I'm going to do, so it's spread out throughout the whole board everywhere, I'm just going to pick a sphere of interest to me. Okay, here's a sphere, and it has some radius capital R. Okay, so this sphere is just an imaginary sphere in my mind, that inside of which is a pile of stuff, and then there's all this stuff outside. There's nothing special at the edge here, but there's some test particle, you could say, of mass m, maybe it's a galaxy, and I would like to track how it moves. Okay, and it's just at some radius r, so we can apply this to any r we want, for any galaxy you're interested in. Okay, or if you just think of it as a bunch of gas, it's just a little chunk of the gas. So I want to know how it evolves, and Newton will tell us the answer. Okay, so maybe let's just put over here a reminder on Newtonian gravity. So if you imagine you had, a bazillion little particles filling this thing, right? There's particles here, there, and everywhere. And actually they're everywhere, so they're outside as well. Okay, Newton, if you treated them as little point particles, the precise equations you would have to solve, you would have to say, well, for the ith particle, or for m, its acceleration is some kind of sum of all the other particles, g, the mass of the other particles over their separation, so the inverse square law. X here, I mean the position of this test mass. So we would, in principle, have to solve those equations. Okay, and do some horrible sum. But we're smoothing this stuff out to treat it homogeneously, so things are going to be nicer than that. We're not going to have to put up with a sum. Okay, we can equivalently, we could write it in sort of the differential form. Right? We can also express Newtonian gravity as the Laplacian of the Newton potential is 4 pi g rho the mass density. And the acceleration here, which is just d2x dt squared, is minus the gradient of the Newton potential. Okay, so we could solve the bottom pair of equations instead. Okay, so that's what we're to do. And now, if you treat this as uniform, who can tell me how I might just, what might this lead to? So let's say the acceleration. Well, let's write it as r double dot. So let's call this the radial acceleration. Is there any nice formula I can write down for this instead of having to put up with those sums or even doing those integrals? Let me give you a hint. I drew this sphere here around this origin. My acceleration, or my r, is relative to this origin. So there's stuff here inside my sphere. So what happens? Yeah. Divergence theorem? Yeah, we could use divergence theorem. And what would it lead to? Do you have, yeah. Do you have a comment? Sorry, say again. You put a rate and yeah.
In the units, the rate and then
yeah. All right. But is there something, what I mean is there something nice I can say about this? I heard divergence theorem. So what does divergence theorem tell us when you have spherical symmetry? What's the nice thing that happens? This thing wants to feel a force, right? And there's all this stuff in green. I indicated the stuff inside the sphere that's pulling on it this way. And there's all this stuff out here that is pulling on it some other way, like this is pulling it that way, and these ones here are pulling it that way. So what's the upshot of all that? Let's see. Should we do it or, yeah? Just like electrodynamics, yeah. Imagine this is just uniform charge, and you want to know what's happening here on a test charge, or say you want to know the electric field at this point. Every shell outside, as Cullen said, doesn't do anything. And it only cares about the stuff inside. So if I take a shell, we could prove it with the divergence theorem. So maybe I'll leave that for the notes if you want. So if you look at a little shell here, you have to do a little bit of a calculation. But, you know, if I look at that shell, there's sort of two competing ideas. On the one hand, you might say, maybe the force provided by this shell on the test mass pulls it that way. It's got to go that way or that way, right, from this shell, because it's not going to go that way. So it may either pull it that way or may pull it that way, or maybe it doesn't do anything. So you might say, well, maybe it pulls it that way because this stuff here is quite close to it. I'm saying it's a 1 over r squared force law. So maybe it should win and pulls it that way. Well, it's this other stuff over here that's pulling it this way is kind of far away. And then the other argument would be there's a lot more stuff to the left than there is to the right. So maybe you should win and pull it to the left. When you have the inverse square law, these exactly cancel. Okay, it's related to the area goes like 4 pi r squared, and the force goes like 1 over r squared, and they exactly cancel. And then furthermore, not only that, so that means that everything outside does nothing. And then what about the stuff inside? Did you already comment on that? Or yeah, Aidan. pulls it towards the center. And what can we say about how much it pulls it towards the center? So let's say we say there's m mass enclosed inside the sphere. What can I write? It's as though it's a point. That's right. Now, do we need a proof of this, or are people happy? Okay. So if anyone needs a refresher, they can look at the notes. But yeah, the divergence theorem allows us to prove that this is just minus g m enclosed over r squared. It's as though this was all at a point. Yeah. That's right. So what we have to do, that's a good question. So yeah, so it sounds a bit funny. I picked this sphere and got some answer. So implicitly, what I'm doing here is that I'm nailing down. So we're at the center. Okay, we want to think of ourselves as the center of the universe, if you like, and we're not moving. So there's all this stuff moving that way, that way, that way, that way, and we're not moving. So it fixes x. The vector here, I called it r, but the vector is also x to our test mass. And once you lock in the meaning of x, you're allowed to run this argument. Okay. So if you wanted to draw a sphere somewhere else, well, you have to rethink the fact that what is your x now? Right? You have to measure the x. There would be an x, say, from there to the center, and then an x to the other points. And you have to do that analysis. Well, you would end up with the same answer. But the simplification here is that I measure everything with respect to we can think of us as an observer at rest, if we like. We could say we're a kind of an inertial observer, and we just run the Newton's laws as usual. So if you had someone out here and you draw a sphere around them, we think they're accelerating. They don't think they're accelerating. We think they're accelerating. So from our point of view, their Newton's laws would be scrambled because Newton's laws look funny in an accelerated frame. Okay. So anyway, the punchline is that it looks simple if we take us as at the center. Yeah, a good exercise to run it for another sphere and see what happens. But you have to be careful because everything is accelerating. All right. So now what I want to do, this formula here is fine, but there will often prove to be a nicer way to express this. So I want to use the fact that the enclosed mass, I want to write down a formula for that. So I'm going to say that the stuff in the universe has some density, mass density, rho m. So that's the mass density of our universe. And when we do GR, we're going to talk a lot about energy density. So I'll say reserve the symbol rho for energy density, and I'll write rho m, good old mass density, nothing fancy. And then to get the enclosed mass, I take the mass density and I multiply by the volume of that sphere. Okay, so there's a prefactor here of 4/3 pi r cubed. Is that all right? So I'm going to trade things for mass density most of the time. Now, although at this point we should say, right, there's stuff inside of this sphere. So as the sphere expands, the mass stays put. Okay, the mass in the sphere at any radius r will just be m. The mass is not appearing or disappearing. There's just a bunch of stars or whatever. They're just staying put. So m is fixed. So you can also invert this equation. And just a reminder that the mass density, therefore, is actually proportional to 1 over r cubed. This is an important thing that we'll need to remember. Nothing too fancy, right? If things double, if the size of the universe doubles, the same number of stars are now in a volume that's 8 times bigger. So the density dropped by a factor of 8. So that's, we should remember this. Is that all right? Most of these quantities on the board, by the way, will be functions of time. So like the density will change. As the universe expands, everything gets more dilute. The density drops by that formula. So R is a function of time, rho is a function of time, and so on. But the enclosed mass is a special case where it won't be in the Newtonian approximation. Okay, so maybe we can try this other board. I had a previous course where I tried one which had a tracker on me. and it would track any motion. So half the time it would just go to someone in the crowd and out the door. It loved the door, but so I gave up on that. So anyway, let's use this formula here. So we get that R double dot minus G 4/3 pi R cubed or R squared. And so R double dot over R, we often like to write it like that, and normalized is minus 4 pi over 3. We got the rho. Rho. Okay. So we have this. So funnily enough, I'm going to call this equation 2, because this is connected to something called the second Friedmann equation. And in a couple of minutes, we're going to get the first one. So the acceleration at r relative to r, so this just has units of 1 over time squared, is minus 4 pi g over 3 times the mass density. Okay, so from this, we can say, right, so as long as we are in a universe, whenever rho, of course, is non-zero, the universe is dynamical. So that's the first thing. So I told you, Newton could have predicted this. The universe has to evolve if you fill it with stuff. That's what gravity guarantees. Now, we don't know, we haven't solved the equation yet, so there are some different possibilities that we'll come to, but it has to evolve. And this isn't a shock, right? We're just doing a glorified version. This mass here is like we're just throwing the apple up. The apple has to do something. Okay, it could be in its upward phase. It could be in its downward phase. It could sit at the top for a moment with velocity 0, so that allows the velocity to be 0. It just says R double dot is non-zero. So if you, at least if you wait a little bit, even if it's momentarily static, it will start evolving yet again. Okay, so things have to evolve. Okay, now that's fine. That's a second order differential equation. But there's actually a first order differential equation we can write down that's often more convenient. So anyone tell me, how could I get a nice first order differential equation? So something just involving R dot, I mean, instead of R double dot. Yeah, dots, by the way, mean time derivative, if it's not clear. Right? But what might I do to get an equation with just R dots? Anything I could do? Integrate? Yeah, maybe. That's possible. I have to know how to do the integral. It's a bit subtle. What's another strategy we often use? Remember, it's okay, let's come back. It's an apple. What do? Physics 101, I throw the apple in the air. What do they say you should think about? What's the other concept we often think about here? Velocity, yeah, well, that's right. Well, velocity is R dot. And then what can I say about it? There's a nice law that it obeys.
Like at their distance, the velocity are going to increase. So there's going to be v and some rate and some distance.
That's right. We could say, we can say the radial acceleration, as I called it, is R double dot. The radial velocity is R dot. And there's a nice law of nature that involves velocities rather than accelerations. You're going to kick yourself when no, nothing fancy. Throw the apple in the air. 50% of Mechanics 101 deals with the following concept. What is the concept? Momentum and the work equation. Okay, we could call the work equation. Conservation of energy. The energy is a nice equation that we can use that just involves velocities. So let's use energy. Okay, so the energy, well, we're just going to write kinetic plus potential. And this is the energy just of our test particle. Okay, I'm not going to talk about the energy of the whole universe. The energy of the test particle. And it's just subject to microscopically just all these forces acting on it. Okay, so energy should be conserved. Okay. Well, it's yeah. So a half m r dot squared, and then the potential energy is like this. Okay, again, it's like the mass were concentrated to a point, even for the energy. And the minus sign, a reminder that it's an attractive force. That's a potential well. Okay, so we have this formula for energy, and this guy is conserved. And so I can use this to solve for r dot, if I like. Okay, let me maybe just write out this second term. Again, using the enclosed mass with this. So I trade it for density. This is minus 4 pi over 3. Like this. Okay, the r cubed, there's an r cubed here, and then I divide it by an r, so I got r squared. All right, so let's summarize that up here. If you rearrange that thing, I want to solve for r dot or r dot squared, let's say. And like I did before in the acceleration equation, it's often convenient to normalize it with respect to r. Okay. You see, the r I don't care about so much, actually, because r was just the distance to a particular test particle. I don't want to make statements about the whole universe, its properties, not whether I chose that galaxy or a galaxy twice as far away. So that factor of 2, for example, would be canceled if you take the ratio. So we sort of care about the normalized acceleration or the normalized velocity. So I'm going to do the same thing. I'm going to divide by r. I can square this. And you just rearrange that bottom equation, and you'll get 8 pi g over 3 rho. And then the correction from the energy term. Is that all right? So I multiply by 2m, I divide by r squared, and I get this. So this is a nice equation. And we'll call this one equation 1. Oh, and I guess I should rotate this. So this one is related to the first Friedmann equation. Yeah, so in general relativity, there's going to be some updates on this law and that law when the stuff is relativistic, as it were. If stuff is moving slowly, GR will collapse to these two equations. Okay, but anyway, this equation is quite nice, and we'll solve this more or less. And now to sort of finally answer your question, in a way, this thing on the left is a very important thing. So we have r dot over r. We're going to write that as Hubble squared, where the Hubble, so-called Hubble parameter, which is h, is just defined as this r dot over r. Okay, so you see it's a quantity that has units of inverse time. So this is a rate, so it's units, and that of rate, or 1 over time. And again, because I normalize by r, so it's not a velocity per se, it's velocity divided by the distance to the object. It will be the same, it's just a function of time now. It doesn't care which object you picked, right? So one that's 100 megaparsecs away or 500 megaparsecs away, that doesn't matter, that's canceling out. This is just some function of time. That's some kind of just property of our universe. Okay, so yeah, so this is you could call this well, this would just be the expansion rate. Now, as I said, generally everything's a function of time. So h is also a function of time. right? So R is a function of t. H will be generically a function of t. And then there's a related thing called the Hubble constant. You might think, well, that depends on time, so it's not much of a constant. But the constant, so to speak, is just the value of it today. So often when I refer to something today, I'll often put like a naught subscript or zero subscript on it, just as a convention. So if you see a naught, it at the very least refers to a particular moment in time, which will often mean today, but maybe sometimes it won't. But it's just a particular reference time, let's say. So this just means h, we could call it of t sub naught by the same idea, or h, if you like, today. That's a particular rate. Okay, and so then this one, these observations tell us that h naught is about 0.7 times 10 to the minus 10 inverse years. Okay. Well, you may have heard of people writing it as 70 kilometers per second per megaparsec. The wild way of writing something that has units of inverse time. So anyway, I will do the conversion for you, and the 7 somehow survive. Anyway, it's about this, 0.7. So it's about inverse 10 to the minus 10 years. Okay, or we can talk relatedly about the Hubble time, which is just defined as the inverse of that. So we can call TH. I'm just going to define it as H0 to the minus 1. And so that's about 1.4 times 10 to the 10 years, which you may know is pretty close to the current age of our universe. And this will not be a coincidence, okay? So just writing H inverse is not literally the current age of the universe. To find that out, you have to do a calculation. But as an order of magnitude, it will not come as a shock that this will come out to be on that same order. Yeah. Actually, there's a slight, there will be a slight subtlety to that, but we can come back to that later. Dark energy acts as a slight wrinkle to that statement. But anyway, so it's just it's a useful time to keep in mind. All right. I wish we had a clock. All right, so I want to talk about solving this equation in the remaining time. Are there any questions about all this? Yeah. So we're about to talk about that, but the answer is no, because what happens if you put your apple on a rocket that was moving more than 11.2 kilometers per second? It would not come down. So if you if you throw an apple beyond that, it goes up forever. So that's what we're going to have to discuss. Yeah. So good. So let's talk about that, and we'll talk maybe about orbits for a minute to get some intuition. So the value of E here, this energy of the particles, is going to dictate qualitatively the fate of this universe. Okay, and so in particular, this E, we don't a priori know whether it's positive or negative or zero. Okay, so just a reminder that negative energy in Newtonian physics is nothing weird, right? The hydrogen atom has an energy of negative 13.6 eV, right? So in fact, bound states in Newtonian physics always have, or the non-relativistic approximation always have negative energy. In relativity, we have to be careful because we have to add an mc squared, so the total energy comes up positive. So that's why I say the kind of Newtonian energy. So let's just think about orbits for a minute before we try to solve that equation for the homogeneous universe. So, if I have the sun here, and let's say we throw in a comet or something, there's essentially one of three things that can happen, right? The thing could just be in some bound orbit, like a regular planet. Okay, like a planet orbiting the sun has an energy that's negative, bound orbit. Everyone okay with that? Energy is the Earth's energy is negative if you delete its mc squared energy. Okay. So the negative potential well beats its kinetic energy. If it was circular, it differs by a factor of 2, you may recall. The potential energy is in magnitude is twice as big as its kinetic energy, but it's more negative. All right, then we can have if we throw in, say, a comet moving very fast, it can just sweep by on some hyperbolic orbit, and it's, say, unbound, and it has positive energy. Well, anyway, if it has positive energy, that's what it will do. Okay, and then there's a borderline case between them, right, which would be obviously E is 0, and it's also technically unbound, but it's right on the edge of being bound in a definite sense. Okay, so not much I can say, I just draw that one too, I guess. But the thing that makes that case special is that, well, let's actually do the top case, right? If E is positive, it's unbound, so it just runs away from the sun. So at late times, its energy is all kinetic, right? Its gravitational potential energy will asymptote to 0, so it's all kinetic. So its kinetic energy has to equal its positive energy. That means it has a non-zero velocity. So asymptotically, this one has a V that is positive. In other words, it asymptotes to a non-zero value. Root 2e over m or whatever. But this one, the special case of E is that it asymptotes to V of 0. Okay, this is at late times. Okay, so that's the special case. So it's right on the edge. So if you give it a slight little tap, you might bump it one way or the other. You just slightly slow it down, and then it will get trapped. All right, so those qualitative statements will all apply for our homogeneous universe, as we can check. So let's see. Any questions about that? Okay, so this differential equation, for generic values of E, we can more or less solve it, but it's actually a bit involved. So maybe I'll give you some tips on the homework. We're going to solve it relatively straightforwardly when E is 0, and then we can describe the other cases. So we're going to do that one here. So case 1 is E equals 0. I mean, we don't a priori know anything about the energy of our universe. So E is just some real number. It could be positive, negative. 0 seems a kind of special case. But as we'll describe going forward, the special case is indeed the most important that we're going to have to deal with. Okay, so then our differential equation becomes r dot over r squared. That term's gone. We have just this term. And I'm going to write this as 8 pi g over 3 rho. But now, okay, I wrote it in terms of the mass density of the universe. But to solve this differential equation, we need to remind ourselves how rho itself is a function of r. Remember I wrote down here somewhere? Remember, rho goes like 1 over r cubed. Right? The universe doubles, the density drops by a factor of 8. Stuff is just spreading out. So we need to know that here to make progress on solving this equation. So what I'm going to do, I want to write rho as 1 over r cubed. Right? So I'm just going to trade this for this factor here. And then there's a trick that we'll often do, the constant proportionality. I'm just going to write it so it guaranteed to be correct, right? So what is the constant proportionality between rho and 1 over r cubed? I can always write it so it's true by construction. So I'm going to write it as rho m comma naught r naught cubed. That's what that is. Is that cool? Do you see what I did there? There's some reference time, let's say. My reference time could be today, whatever. I call the density rho m with a naught subscript. And that test particle is at some radius, which today is r naught. So you see, by definition, this equals this today. Is that clear? When r equals r naught, which is today, rho is rho m naught. Satisfied with that way of doing things. It's just a way of writing things. So it's you gobble up the constant proportionality in a way that's manifestly true. Yeah. Is there a question? Or no? No, just people cool with that? So anyway, so but the 1 over r cubed is actually the most important aspect of this. Okay. So we can solve for r dot. Remember, this is dr dt. And this is then going to be, you have to take a square root, so there's some plus or minus. There's all these constants that I'll just call big capital C times 1 over root r. Right, where C is just some constant. Okay, so that's our differential equation. It's not too bad. dr dt just goes like 1 over root r. Now there's a plus or minus. Okay. So this has a good meaning. Why is there a plus or minus? What does that refer to? Right, remember I took the square root, so that's why I got a plus or minus possibilities. So what would the minus mean? Like, okay, remember this is the velocity, the radial velocity. What if it's negative, right? It's just things are moving in. So it's telling us there are these two options. Like we said, we throw the ball up, it may go up, it may go down. And now this is E is equal to 0. So this we're going to see is connected to this special case. But we don't know if we're on the, so the analogy therefore is that we're throwing this thing at exactly 11.2 kilometers per second. We're at exactly the escape speed. That's what E is 0, which is the case I'm doing. Okay, so if you throw a ball at exactly the escape speed, it runs away and asymptotes to 0 velocity. That's the plus. There's another solution where that ball just came in from infinity and then landed, came to the Earth, the exact time reversal. Okay, so we have both solutions, right, which you could say is due to time reversal symmetry. So any solution you can find, you can always time reverse and get another solution. That's what the plus minus is. So that's because gravity, and indeed in general relativity, has time reversal symmetry. So we have to pick the solution that we care about, and we only care about the plus because we know as a fact our universe is expanding and not contracting. So that's the solution we pick. But we could not a priori know that it should be expanding rather than contracting unless we had some other reasoning. Like our reasoning could be that we don't like the fact that in the past the universe was this infinitely big thing that was coming in. That might be a funny way to start a universe. So, but that would be an additional argument. Okay. But anyway, we're going to pick the plus. Okay, so this kind of equation, how do we solve this kind of differential equation? What do you do to solve these kind of equations? dr dt is some function of r. So what do you do? Yeah.
Separate.
Right. Yep. Thank you. So we just do separation of variables. So I'm going to write root r dr is this constant dt, and then I put an integral on both sides. focused on the plus only. And then I should put some endpoints of my integrals. Okay, so we can say, well, we're integrating to r at time t. That's fair enough. That's kind of what it means. When you're at r, that's at time t. That's kind of what it means. Right? R is a function of t. Right? Strictly speaking, when you do this, the r's here and the r there should not be the same thing. So you might make them some dummy variables if you want to be fancy. Doesn't matter. And then we have to decide on the lower endpoint of the integral. Okay? So I could just say, it'd not be wrong to say at some r1, I start at t1. I mean, that's a fine thing to say. But we're actually going to push it a little bit more than that. I'm going to push the lower endpoint down to 0. Okay. We're going to imagine that this is true all the way back. If it's expanding, we can just keep going back, back, back. Inevitably, these equations will persist all the way down to r of 0. That's when we'll stop. And we'll call that t is equal to 0. Okay. So r equals 0, which we'll call t is equal to 0, and the Big Bang. Okay. Separation between everything is 0. The density, which is 1 over r cubed, will be infinite. So we'll stop at that point. Okay, so anyway, we have this simple integrals now. I'll write it over here. So we have r to the 3 halves, right? And some 2/3 equals c t. Okay. Or r equals some constant t to the 2/3. So what we really care about is the t to the 2/3. Right, there's some c floating around, okay. But again, these constants of proportionality, it's often fruitful just to make it obvious that it's correct. So I know that r of t is t to the 2/3. And I don't want to drag around these c's like that. I could. I'm going to write it like this. T naught, r naught. That's equivalent. Is that okay? So this is our result. Okay, so this is how the universe expands if the particles have the Newtonian energy is 0. It grows like time to the 2/3. We can plot that here. There it is, t to the 2/3. And here 0, again, is our Big Bang. Let's also look for now at actually the velocity, not the Hubble rate. I'll look at literally the velocity this time. So r dot, it's useful. We could take the ratio to get Hubble. Maybe we'll worry about that next week. Well, could easily compute Hubble. So r dot, let's just write it over here, is, well, there's some prefactors, 2/3, r naught, t naught to the 2/3. Fine. But what I really care about is the fact that you have to take t to the 2/3 and differentiate. So you get t to the minus 1/3. So the velocity decreases in time. So r dot looks like this. It's not a great plot, but you get the idea. Something like that. So we recover the E equals 0 special case as I described for, say, comets in the solar system, right? They come in, they go out, they're not bound, right? This thing keeps expanding forever, so it's unbound. But it has the special case that its asymptotic velocity is going to 0. So it's slowing, slowing, slowing. never quite comes to rest, but is asymptoting to rest. All right, so any questions about this? You look. Yeah. Well, but I solved the homogeneous case. I just give, yeah. But the bound analogy works pretty well. It's just the analogy. Okay, so let me now state, as I said, solving the full equation for non-zero E is a bit of work. And actually, well, it turns out you can only solve it in terms of elementary functions. You have to change the time variable to some other time variable and so on. So we can worry about all that later. But let's talk about we can nevertheless more or less solve it qualitatively. And I'll do case 2 now. So case 2, I'll consider positive energy. There's the eraser. Better put that back in. Since my battery is dying on my laptop. Oh, I broke the thing. Jesus. We can edit this part out. Look at that. Is anyone? All right. I think, no, actually, I think I have my extension cord. Okay. Okay, so that's the mass term. Again, a mass density term. Once again, it's 1 over r cubed. And now let me write the other one. So if we stare at this equation, we can get a good clue as to what's going to happen. You can first wonder what happens at early times. Right? It was r goes to 0 at the Big Bang. Because in that case, if r is small, you see this term, the one that we just focused on, actually still dominates the correction. Because this is 1 over r cubed versus 1 over r squared. Okay, so the analysis we just did applies at early times. Is that all right? This one dominates at small r or small or early t. Okay, but then, so we're going to go on some t to the 2/3 trajectory for a while, and r is going to get bigger and bigger and bigger. And as r gets bigger and bigger and bigger, then we can't ignore this term eventually. And in fact, surely this, if it's unbound for t e is 0, it's going to be unbound for positive e. So r is going to keep growing. And that means at late times, this term is then going to dominate over that term. It will be the opposite at large r. Okay, so this dominates at large r or large t, late times. Okay, so we already solved the early time behavior. It's t to the 2/3. We can just solve for the late time behavior, and then we just sort of match them to each other. Well, just qualitatively. And you see at late time, it's very simple. At late times, r dot over r squared is then just approximately this term, 2e over m, 1 over r squared. So it's a very nice equation because the r's cancel. See, there's an r squared here and an r squared there. So this just says that r dot is, well, approximately root 2e over m. R dot is a constant. So the velocity asymptotes to a constant. just like our orbits in the solar system do, unbound orbits. Or R equals root 2e over m times t, up to a constant, but that will do. Okay, so R just grows in time t. So we can add that here. Yeah. So this was the, let's say, E equals 0 case. So this new case where the energy is positive hugs this curve for a while. The early times we said it's the same analysis. And then it's going to deviate eventually to a straight line proportional to t. Okay. And if E was very small, it would hug it for a very, very long time and then eventually deviate. So when it deviates depends on the value of E, right? It's just roughly when these two terms balance is when it starts to deviate. Okay, so this is qualitatively the E greater than 0. Here it's proportional to t. We're out of time, but let me just say last comment then. If I do the E negative, finally, so let me put a minus sign here with a, I don't know, absolute value. I mean, this term's definitively negative. This late time argument fails now. You can't push R to be large because then this whole thing would be negative and you'd have a positive quantity equals a negative quantity. That doesn't work. You can imagine it should be a bound orbit, so it probably doesn't want to go to large R, but we should check. So instead, because of the minus sign, right? Again, early times this will dominate. It'll be t to the 2/3. R is small. As R gets bigger, eventually they balance and the difference goes to 0. So there'll be a critical R. The critical R is just when that minus that equals 0. You can solve for R critical if you like. That's when the velocity vanishes. And so that's just the same as this eraser that went up and there was a moment where R dot was 0. And then after that, for sure, it falls. Okay? So in that case, looks like this. Goes up, hugs t to the 2/3, then deviates at there's some RC, where the right-hand side equals 0. And then it does the same thing on the other side. It does the inverse. And then down here, we will call that the big crunch. The universe collapses. Yeah, so this is E negative energy. T to the 2/3 initially for all of them. So that's what happens in a Newtonian universe. And it's accurate, as I said, for the first maybe 6 billion, well, most of the first 6 billion years of our universe, these curves are correct, except we need to know what E is. A priori, you probably should guess that E is, if you're a particle physicist, you probably guess that E is non-zero. I don't know. Because like in the standard model, for example, every parameter, more or less, every parameter that could be non-zero is non-zero. They seem to be non-zero. This is just some random parameter E. It could be some, it could be 17 joules or 2 billion joules or minus 5 joules. Seems a bit unlikely that it would be 0. And yet, as we'll discuss next time, it looks like it's 0. So that's something strange. Okay, any questions? All right, we'll see you then next week. Thank you.